When we speak of system security, we refer to its ability to withstand overloads and disturbances.
The power system is considered to be operating normally when all of the equipment is operating within its specified rating, all parts of the system are working well within their stability limits, that is, the power angle is low, voltage levels are correct throughout the system, frequency is correct, and sufficient reserve generation capacity is online to accommodate load changes, and interchange between neighboring utilities is as scheduled. Unfortunately, these ideal conditions are often disturbed by equipment outages, both planned and unplanned. For example, a generator outage for maintenance could result in lower bus voltage locally due to loss of reactive power. Increased generation in some other part of the system, which may bring certain transmission lines closer to their stability limit. Possible reduction in exported energy to a neighboring utility. Increased generation costs, as more expensive generation units will need to be placed in service. Outage of transmission lines will also cause problems due to redistribution of the load flow throughout the rest of the system. This may bring problems of low voltage in some areas and may also cause the power angle to approach the stability limit on certain transmission lines.
Of course, a certain amount of reserve is built into the system. And generally speaking, a planned outage of a single generator or a single transmission line would not normally weaken the system significantly.
However, the system operator has to be concerned with the possibility that while the system is operating in this weakened condition, a sudden forced outage may occur. This could be, say, an interruption due to a fault tripping a transmission line out of service. So we need to know just how this hypothetical second outage would affect the stability of the system, the interchange, and the voltage. These what-if questions are answered ahead of time by examining many different hypothetical situations through what is known as a contingency analysis. The answers are tabulated for ready reference by the operator, usually on a computer screen. So before permitting any requested outage to take place, this information enables the system operator to rearrange load flows around the system and perhaps modify the interchange commitment. All of this highlights the necessity for good planning and advance notice of any outage requirements. Even with a planned outage in progress, the system is still considered to be operating normally, as the system operator is able to arrange the system to accommodate this.
Indeed, if you think about it, I'm sure you'll agree that on your own power system, there's always at least one major item of equipment out of service at any given time.
However, if a forced outage did actually occur under these conditions, the operator would move to a state of alert, as the system would now be considered abnormal. On most power systems, this one forced outage would not cause an entire system upset. But this abnormal operating condition may leave the system in a weakened state. The system operator will try to place the line back in service as soon as possible, or once again, rearrange the system conditions so as to reduce potential for further problems. However, supposing that yet another forced outage occurred before the line could be restored, now we have 3 outages. This system is now said to be in an emergency state. Some parts of the system may become severely overloaded and approach stability limits. It is likely that the system would not survive yet another additional forced outage. This would probably result in a cascading effect, with the consequence that generators and lines trip out due to instability. The system would probably split into several disconnected islands, some with an excess of generation, some with a deficiency of generation, and perhaps other areas with no generation at all and hence a blackout. The AGC would have to be taken out of service. Otherwise, it may try to control generation in areas which are separated from its frequency measurement. In practice, the AGC is disconnected automatically when frequency falls to 59.8 hertz or increases to 60.2 hertz.
In this situation, the operator obviously has his hands full, and perhaps some hours may pass before the system can be restored to normal. In order to prevent this disastrous and dramatic turn of events, the system operator must endeavor to keep the system fully intact as far as possible. We can all help with this.
Maintenance outages should be kept as short as possible so that equipment is returned to service within the minimum time period. If any testing is to be carried out on live equipment, for example, protection schemes, the system operator must be fully informed of the activity so that he can take precautions against any possible mishap. If a line does trip out of service, the system operator will want to reclose that line as soon as possible. Of course, the reclosing relays will normally take care of this in the case of a temporary fault. You'll remember that we have discussed the role of reclosing relays in regard to system stability in an earlier tape in this series. However, if the reclosing relay locks out due to a permanent fault, cooperation will be needed with the relay department to decide the next move. Clearly, correct operation of protective schemes is a vital element in maintaining a stable power system. In order to carry out his functions efficiently, the system operator must have good communications with the major stations around the system. He also needs minute-to-minute information to indicate the status of the equipment and the conditions at all locations. All of this information is provided in the Energy Control Center. Data is transmitted by telemetry over the various communication networks and is displayed in various forms. For example, the operator reads information from a computer printout, from CRT screens, from recording charts, and from indicating meters. Quite often, line loadings are indicated on a large wall map, but more detailed information is available on the CRT screens. Typically, for any particular bus, the operator can view the status of equipment, that is, breakers closed or open, bus voltage, bus phase angle in comparison with the system reference bus, power and reactive loadings, including direction on connected equipment such as generator, lines, etc. The system frequency will be indicated on a wide range, say 55 to 65 hertz, as well as on an expanded scale over a smaller range, such as 59.5 to 60.5 hertz. The wide-range frequency scale might be necessary to record large frequency swings during very severe disturbances. One section of the control room will display information related to interchange with neighboring utilities. Often a large TV screen will provide up-to-date weather maps and forecasts. Other indications relate to the automatic generation control equipment, including area control error and primary demand, that is, load. In this control room, we also have the time deviation indicated. The display of information will probably be laid out in a logistical manner to suit the division of work within the control room. As we previously mentioned, the system control operation actually requires several individuals. For example, generator dispatcher, interchange operator, system security.
Clearly, successful operation of the power system depends upon complete cooperation between all parties. That is, the system operators, plant operators, substation operators, maintenance personnel, communications personnel, and relay technicians and engineers.